Thanks everyone for being here for our third session in concrete culture. This afternoon is called What We Might Do. I'm Judith Young, one of the co-organizers of this, along with Stuart Hicks. This afternoon's session will be moderated by Thomas Leslie, following presentations by Ted Fishman, Benton Johnson, Roger Hubeli, and Caitlin Mueller. But I first want to introduce Tom Leslie. He's an architect who teaches building science, history, and design at the University of Illinois Urbana-Champaign, although he lives in Chicago. Since practicing with Norman Foster and partners in London, which he has in similar, I don't know if you all have talked, Martin and Tom, about both working for Norman Foster, sorry. Since practicing with Norman Foster and partners in London, he has held appointments at the University of Technology, Sydney, Bauhaus Universität Weimar, Università de Bologna, Iowa State University, and Northwestern University. Leslie's the author of Chicago Skyscrapers, 1871 to 1934, Beauty's Rigor, Patterns of Production in the Work of Pier Luigi Nervi, and Chicago Skyscrapers 1934 to 1986, which received the 2024 Pattis Family Foundation Chicago Book Award from the Newberry Library. He was the Booth Family Rome Prize Fellow in Historic Preservation at the American Academy in Rome in 2013 to 2014. Please join me in welcoming Tom Leslie.
Great, thank you, Judith. Honored to be moderating this session. Congratulations, we have made it to the future. We've agreed that the order, for reasons that maybe will be clear, Benton Johnson will go first, Roger Hubeli, Caitlin, and then Ted. Ted will bring us home. So Benton Johnson is a structural engineer at SOM. He brings new technologies and approaches to the fields of structural engineering and sustainable design. He has led the firm's multi-year timber tower research project, advancing full-scale testing of mass timber systems, and has pioneered 3D printed building innovations in collaboration with Oak Ridge National Laboratory and the U.S. Army Corps of Engineers. His work transforms experimental ideas into practical, efficient, and sustainable solutions across building typologies. At 100 Mount Street in Sydney, he directed the design of an exposed mega bracing system that reduced cost and carbon while maximizing leasable space. Please welcome Benton Johnson.
Well, thank you for that. I hope you all enjoy some of the slides we have prepared for you today. There was a lot of talk about timber in there, but we're going to be focusing on the concrete side, and of course, research and innovation along the way. Concrete is not a new material. We all know this. There's a lot to do about Roman concrete and its qualities and why it's lasted so long. And it's true, there's a lot of interesting properties associated with it, but one of the reasons why it had lasted so long was that material was being really utilized in a way that makes most sense for what concrete is. Ultimately, concrete is a compressive material. It's rocks bearing on other rocks. The cement is what holds it together, but ultimately it's that aggregate interlock and pushing against each other in compressive forces that makes it work. And actually the lack of reinforcing in a lot of these structures is why they were able to last for so long, because corrosion of the reinforcing is ultimately the downfall of a lot of concrete structures we see today. One of my favorite buildings out there is the Ingalls building in Cincinnati, Ohio. I did a project in Cincinnati. I was traveling there all the time, so I got to go check it out. It's been recently renovated into a hotel. When built in 1903, it was 16 stories tall, and people could not believe that concrete could support its own mass because it's so heavy. And so there's stories about this entire building being built on shores all the way to the top. And they knew the date that they were going to pull those shores to see if it could support its own weight. And there were photographers lined around the streets to get that photo of this thing collapsing in on itself, which of course did not happen. It's a very interesting building. Recommend you check it all out now that it's a hotel. But a great case study in why concrete makes sense in a vertical application, because of its compressive nature. Stacking concrete and load bearing in a compressive way on columns makes a lot of sense. And of course, the sky's the limit now with Burj Khalifa, tallest building in the world. I was super fortunate to work on that project, like my first day in the office at SOM. My boss at the time was very dramatic. He's like, all right, we got to deal with all these RFIs. We got to make these things happen. And it was very exciting. I did not take part in the first design. As Tom mentioned yesterday, buildings get designed twice, once in design and once in CA. I was still in college working on the project on the left. So we were studying some special connections for reinforced concrete shear walls for seismic ductility. And of course, the Burj has a million shear walls in it, so it makes a lot of sense to go from that application to that application. Although I did not do that, I worked on the steel parts. I was part of the second design in CA, helping figure out all this complicated geometry and the steel connections after the fact. So the Burj transitions from a concrete structure to a steel structure at one point. And the construction technologies that I'll talk about today that are enabling more and more concrete construction to happen will illustrate why that building transitions to steel at some point. Yesterday I liked the mixture proportions, very simple for concrete. I believe it was 1 part cement, 2 parts sand, and 4 parts aggregate. And if you all know that water is a very important part of the concrete mixture, you have a half a part of water. That water to cement ratio is really important. But ultimately, at the end of the day, it's rocks bearing on rocks in compression. I mean, that's what concrete is. The cement and all the rest of it is just trying to prevent it from bursting. It's to prevent those rocks from slipping away from each other and splitting as you go through. So that cement is really just something that enables the full capacity of what that concrete can be. And so as we've developed concrete even further, I think the other things that go into it, the things that you measure in the 1/10 of a part, the 1/100th of a part, are so critical. And that would be the admixtures. I ripped this image from Euclid Chemical. I don't know if these are actually admixtures, but the amount of chemistry that goes into concrete mixes now is incredible. We know we want to drive down the water to cement ratio, so it makes a very stiff mix that's hard to work with. And so to overcome that, we put in plasticizers, super plasticizers, things that make it flow as it goes through. Sometimes we want the concrete to go slower because we might deliver it in New York City, so we put retarders into that mix to slow down the chemical reaction. Sometimes we put accelerators into it to speed up that chemical reaction so that it can gain strength sooner. Sometimes you put shrinkage compensating admixtures or air entraining admixtures. I could go on and on and on of all the things that you put into concrete now to make it what it is. And as a result, there are machines like this out here that when you order your ready-mix concrete, you pick the 3, 4, 7 different admixtures that are going into it with all of these basic parts along the way. And that's what allows us to get the concrete into buildings and why it's sort of taken over. So to illustrate this, I want to talk about a building that's in construction here in Chicago now, 220 Ada. We've been working on this project for quite some time. It's now topped off. But I would say this is really a state-of-art building and how concrete construction is done here in Chicago today. This is a job site photo of pouring one of the parking decks. And what you'll see here is no buckets dropping concrete down onto the decks. What you'll see is this long articulated arm with a hose that's just pumping that concrete where it ought to go. On the left-hand side of the core, you can see a white slick line. That's the pipe where they're pumping all of that concrete onto that deck. And so when you think about why concrete construction has gained so much popularity, it's because of the automation of it and the ease of putting it up in the air. The heaviest thing about any building is its concrete floor slabs. And with concrete technology, now you pump it to the top. You're no longer reliant on that crane, which is very slow to get materials at the top. And at the top of the core, you can also see it's advancing. It's a self-advancing formwork, similar to the slip form technology that was talked about for Marina City. But now you have these technologies that allow it to push forward and not rely so much on the crane to move ahead. And so as that building is going up, you just got the concrete trucks parked up. And they're not dumping it into a hopper, they're dumping it into a bin that's going and pumping it up to the top. So you have continuous concrete placement from start to finish. Watching these buildings go up is incredible. The tradesmen have an unbelievable amount of knowledge that you do not get in the design studios. Each one of these floors takes 3 business days to build. Day 1, they build the formwork. Day 2, they put the reinforcing. Day 3, they pour the concrete, and then they start again. 3 days at a time. All incorporated in that is all of the in-floor plumbing, the conduit. It is an amazing dance of all these different trades working together. And so to that end, concrete materials the strengths have become really important, but it's become that high early strength that we care most about. This building has concrete slabs that have 8,750 PSI strength, stronger than any of the concrete in Marina City. And it's being done so that they can stress those tendons and advance as quickly as possible. The strength of concrete that we use just in a horizontal application was the dream of the concrete industry to go vertical just a few decades ago. Another innovation has been just about stripping away anything that slows us down. This is a photograph not of 220 Ada Street, but another prominent project here in the city, where the concrete slabs wanted to be a 5,000 PSI mix, but the vertical concrete wanted to be a 14,000 PSI mix. And if you have a concrete column and interrupt it by a floor, that 14,000 PSI concrete column will crush that 5,000 PSI floor. So what they do is a pretty rudimentary strategy here, which is they get a bucket of 14,000 PSI and they dump it where the column goes while they're pouring the floor slabs. And if you look at that column stack as it goes up, you'll see a discoloration between a lightly colored gray, that is the 5,000 PSI concrete, and a more darkly colored mushroom, as they would call it in Australia, of the 14,000 PSI concrete. And that's how you go up. But that it really slows things down. A friend of mine, Paul James, would say that puts sand in the gears. That's a Paul James saying. You got to get the sand out of the gears, is what he would say. And so, looking ahead, when you go tall, much taller than 220 Ada, you really need to activate that amount of concrete strength. So now I'd like to talk a little bit about 400 Lakeshore Drive, the building on the right that's under construction now. The tower to the left is a future phase. As many people know, this is the former Spire site, and there's a cofferdam down there. This is our foundation where we put the square peg in the round hole to activate those foundations as the element goes up. What I find interesting about this image is to build that cofferdam, you have structural steel, sheet piling that holds the hole open, but it wants to collapse in on itself. And so you'll see these horizontal bands of concrete that act as compression rings that keep that hole open. So it's being used in the right application. And this hole is down several stories. Obviously, you can see how small those individuals are. So if you're a concrete contractor, how are you going to get concrete down there? You dump it in the hole, right? I mean, you just drive up and you dump it in the hole. Not so much, though, because with all of these different admixtures that we placed into concrete, you're now at risk for something that we call segregation, where you'll actually get separation of the aggregates and all the other constituent parts because of all of those different chemicals that we put into them. So you really do not want to just throw concrete down a hole when it's a high-performance material. You want it to be controlled. So even though it's the simplest thing in the world, drive a truck up and dump the concrete in a hole, we still choose to pump it so that we can place it precisely as it goes through to avoid those kind of challenges. And here's that construction process as it goes up. The same criteria. This is a 3-day cycle as it goes up, post-tensioned and all the rest of it. But in this building, we're actually using 10,000 PSI concrete on the lower level slabs to avoid all of those puddling, to avoid all that mushrooming. So the innovations over and over and over again to say, allow us to use those 15,000, 16,000 PSI mixes. Now we tune the floors and the columns because it's about speed of delivery that is really the key to success on these buildings. So when I think about all the concrete innovations that got us here today, I put them into kind of like 4 major groups. I'd say concrete performance and high strength concrete, post-tensioning cables, the ability to pump concrete so you don't have to rely on the crane, and self-advancing semi-autonomous formwork systems that climb up the building and get it built. And so that's kind of an obvious corollary to what I'm going to talk about next, which is 3D printing generally, but concrete specifically. This is an image of 3D printing at Oak Ridge National Laboratory. So this is a carbon fiber reinforced ABS material that we did as a demonstration project for the DOE. And we 3D printed that building on the left in a bunch of different segments and then post-tensioned it together for good measure. We 3D printed that little staircase that you go up there, and we 3D printed that Jeep as well. You can see the oak leaf on it there. At the time, it was a really nice reunion because Phil Enquist, who was the governor chair at the time, we pulled together all this great imagery from back when SOM was young and built, helped design the Oak Ridge campus. And so it was this kind of reunion of these old firms. And as an out from this effort, we put on an exhibition at the National Building Museum called Secret Cities about the development of Oak Ridge and the atomic bomb. So as a result of that collaboration, we got another government contract for the U.S. Army Corps of Engineers. And this is at the Construction Engineering Research Laboratory, which is right there at the UIUC campus. And there's a lot of changeover between the UIUC campus. And they approached us to say, look, we've been experimenting with 3D printed concretes, and we'd really like for a design firm like you to take a look at it from from a first principle standpoint, talk about code development, how we could get this thing over the line. They had already 3D printed this building, which we were not involved with, and they built it inside of a shed. So it's protected by the wind, right? So it's protected. Straight extrusion walls, got a wood roof on it, all that kind of stuff, and it's got these really crude connectors around the outside. And so when they engaged with us at SOM, we looked at a lot of different approaches on how we could do this, but the first thing we asked is, okay, what are the limits? What can we break about your 3D printing process, and how can we create forms that might be more efficient and optimum? And so what we did is we came up with this building form for their building there, which would be a series of self-stable walls. And this would allow you to create a building structure in any kind of configuration that doesn't have to rely on the diaphragm for stability, so that every individual wall is self-stable. And the nice thing about that is that when you talk about 3D printing, you just want to show up and do it, right? You don't want to have all these other systems that it relies on, so it unencumbers the concrete walls from the rest of the building systems to support itself. And so we wanted to do this demonstration, which was a 24-hour print. We were going to start at 10 in the morning and go to 10 in the morning the next day to show and demonstrate this technology. This was this first run. You can see this morphing wall that starts as a corrugated pattern is going to go up to a straight wall at the top. And it was damn hot that day. I mean, it was not fun. And you can see the concrete mix there is kind of slumping a bit, right? And you can see all this kind of purple curing and sealing compound on there. The trick of 3D printed concrete is really not the robotics, it's the material science. How do you get concrete to sit on concrete that has just been placed so it doesn't smush everywhere, but it's got to be liquid enough that it forms a bond, and then you got to run ahead. So it was difficult during the day, and then it was tough during the night. This was the operation. You can see the printing that's happening on the left there. The Sunbelt Rentals, they're loading it in. On the right-hand side, beyond the tent, that's their admixture apparatus that would put all these things. I climbed up on some like old barrels to take this photo. It was like midnight. Just watching them go ahead, it was pretty incredible. The Army Corps called in the Marines to help because they wanted to have it kind of like on-the-job training. And so these guys like had never really done any 3D printing, but they were like, we want to come in and take care of this. So I love this photo because you can see the digital process as it's going through, and then you can see the printing that's happening simultaneously, this digital and physical happening at the same time. The individual on the upper right-hand corner, he is civilian Army Corps, and he is one of the individuals that's leading the code development on 3D printed concrete now. And we printed through the night. And so this was dawn. And I got up on a ladder to try to get this perfectly, and I was on there with my cell phone. I'm like, I got to get this line of printing exactly perfect with the sun coming up, and Captain Friedel in the back there. What he's doing is he's actually controlling the speed of the printing, because depending on the quality of the mix, if it's too loose, if it's too tight, you got to go faster or slower. And so he was driving the ship by the time we got through the morning. And that's what it looked like after the fact. Pretty rough. 3D printed concrete has come a long way, but I think a really nice demonstration about what can happen next. In Eaker's talk, he was talking about the fabric forms and the plastic forms and all these different things. And it really is new technology that drives new architectural forms. And certainly 3D printing concrete is a very attractive option moving forward. We talked a little bit about admixtures. We talked about cements and parts. I did want to pause and talk a little bit about cement replacement. Cement is actually the problem when it comes with concrete from a sustainability standpoint. Most of the embodied carbon footprint in concrete comes from cement production. And so that is a big reason why we try to minimize how much cement we have in them, but also replace it. On the left-hand side is ground granulated blast furnace slag. That comes a byproduct of creating steel. In the middle, we have silica fume, which is a byproduct of creating silica components. And on the right-hand side, you've got fly ash, which is a byproduct of burning coal. And so all those things are pretty tough. And so putting those things together, we've been working with other companies on how to do things, like Cyoneer. They're looking at kind of replacing silica fume by using ground glass, now recycled glass, to get it down to its constituent parts as a cement replacement, and get that carbon out of there as a waste product from another industry, but it's not a waste product from an industry that's burning coal, I'll say. And then biochar is another thing that we've been looking at. This is an image from MIT's website that we've been looking at some startups. I did want to talk a little bit about another company, Prometheus Materials. They're looking at using algae-based cement replacement, where you grow this algae, you dry it out, you grind it up just like the others, and then you add in some other components and you get this cement. At the biennial a couple of years ago, we wanted to showcase this with a pavilion we called the BioBlock Spiral. We used some research that we had excuse me, on some test builds, using it as a block form. It could be used as concrete, but we studied as a block there in an exterior application. And then for the biennial, we went ahead and built a demonstration pavilion in the Fulton Market area, where we wanted to look at the acoustic properties of this material. It's more acoustically absorbent than traditional cement, so we looked at some different forms and settled with this spiral here. And although it's a unique material, it goes together just like conventional blocks. And here's just some construction photos of it going through. It's got an earthy smell to it when you're making algae-based cements, and that's that. And lastly, I wanted to talk about just two other things. We're talking a lot about concrete buildings and concrete frames, but concrete is everywhere, and it is ubiquitous. This is a very well-known building in the city, obviously out of structural steel. And if I go back to the idea about how concrete is made with the one part this and one part that, by weight, this is 2-part steel and 3-part concrete. There are lightweight concrete slabs in this building, but most of the mass comes from those slabs and not the structural steel frame. Here's an image of level 16 about ready to get poured with all the rebar in there, and you can see the formwork that's placed in there. It wasn't using composite metal deck. And so if you think about that steel beam, it's there to hold up that heavy concrete slab. That steel beam is being held up by a steel column. That steel column is being braced by the steel mega bracing, but all of the steel mega bracing is holding up the columns, holding up the beams, holding up the slab. It's the slab where you have the most of that mass, and so we try to attack that as a material to try to make more efficient, including on timber construction. Concrete is great because it has really nice acoustic properties. There's a building of ours in California where, although it's an overall mass timber frame, we have non-structural concrete topping slabs that help you level out the floor, put out electrical boxes, and give you some other nice benefits, but it was not made structural. And so looking forward about concrete, it's not just about, in my opinion, concrete frames, it's concrete in all of its applications. And so we've been doing a lot of first-hand research on timber concrete composites, where we actually look at taking a timber element and then reinforcing it with a concrete slab with specialized connectors so that we can both increase the performance of timber structures to be more compatible with other building frames while still using less and less concrete along the way. Okay, that's what I had for you. Thank you.
Great, thank you, Benton. Our next presenter is Roger Hubeli of APTUM Architecture. He has expertise in material technology, tectonics, and construction. His current research revolves around advanced concrete technologies, most notably through collaborations with CEMEX R&D and the NCMA. APTUM has received numerous design awards, including 2 AIA-NY Project Merit Awards and a 2018 Architect Magazine R&D Award. His work has been exhibited and published in prominent print and online publications such as Architect Magazine, Domus, Oculus Magazine, Interni Magazine, Competitions, Architect, Bustler, Architect's Newspaper, Arc Daily, Frame, Design Boom, and others. I can't think of many others offhand. Roger is a member of the Swiss Architecture and Engineering Association, SIA, and he holds a master's degree from the ETH in Zurich. So, Roger.
Well, first of all, thank you very much for having me. It's been really amazing to see these presentations and the amazing work that is getting done. Building materials are subject not only to their physical characteristics, but to the ways in which we collectively perceive, narrate, and deploy them. Wood is persistently described as natural and nurturing, steel as strong and efficient, and concrete has a long history of oscillating between the expressive promise of the future or being relegated to the unpleasant, inflexible, or the merely utilitarian. These perceptions are not simply descriptive, they are formative. Material narratives are constructed through the entanglement of policy, industry, design history, and the ongoing challenges and crises of our time. And while I feel absolutely unqualified, just to be very clear, to predict what we might do in the future, I have no clue, I do believe in the might of actually just doing to help to shape these narratives. We are focusing on concrete. This, as crude as it might look, is actually a UHPC mix. We are focusing on concrete because of its unprecedented formal freedom and control, its role as the vector for the promise of an unprecedented future supported by a complex global infrastructure, but also as a symbol for environmental degradation, failed social housing policies, or aesthetic contempt. It is precisely at this intersection between ambition, necessity, and critique that the possibility arises for revisiting and revising its terms. As designers, we are interested to explore this through the material itself. Just as William Blake, we argue that the true method of knowledge lies within experiences and experiments. In reference to yesterday's session, though, I want to say that we try to experiment in a non-angry state. And in this talk, I will try to make this argument by showcasing how we are questioning the typical mediation of concrete in our experiments and experiences in search of new terms and the future for concrete. If concrete is often constructed culturally as opaque, thick, and heavy, what rules or possibilities might be discovered if instead we pursue thinness and transparency or buoyancy? If its performative strength, this is like, I don't know if I can, it's a bit, try to ignore the talk. Pursue thinness, transparency, or buoyancy. If its performative strengths are presumed to lie exclusively in mass and inertia, what new design sensibilities emerge when fragility, delicacy, or movement are foregrounded? Such an inversion is not denial of fact, but rather an opening onto new contingencies, new ways of working with, rather than in opposition to the material's inherent logics. It must be said, though, nothing in this domain can proceed without profound collaborations. The research and prototypes shared in this talk owe a really great gratitude to industrial partners, especially Cemex R&D, whose expertise, resources, and willingness actually to work at the intersection between complete speculation, what we do, and the kind of industrial reality that they serve have been absolutely crucial. And despite their role as an R&D for a very large corporation, can actually not be taken for granted. And what follows, I will present three approaches that are each based on concrete mix technology that alter the typical standard reinforced concrete towards a specific performance. Broadly, the first is the idea of thinness. It's slender and delicate and based on an increase of flexural strength of the mix. The second, Risolith Island, explores buoyancy and the delicacy, and is based on mixes that focus on density and porosity. And the third, Sixoform, is working with foldable concrete that is made possible by precise control of mix workability, each intended to be an experiment in the reimagination of concrete's agency. We see these investigations not merely as a formal exercise or technological demonstrations. Each is a proposition about how we might draw other futures into the scope of our present moment. Digital fabrication, environmental performance, and the tectonics of assembly are treated here not only as means to an end, but as sites where material, form, and environmental context dynamically negotiate with each other in real time. In collaboration with CEMEX, R&D for an exhibition at the California College of the Arts in San Francisco, we developed this small pavilion called Thinness, an ultra-thin concrete pavilion that pushes spatial structure to its limits. Here, structural capacity is achieved by a skin whose very thinness redefines its strength principles. Cuts articulating the about 1.5 inch thin vaulted surface are designed to dramatize the skin as structure, here compared to a kind of typical concrete wall at the same scale, marking a deliberate shift from the traditional massy volumetric conception of the concrete toward the filigree, tactile, and fragile. Similarly, when a column 9 feet in height can be carried by 2 people, the act destabilizes deep-seated associations of the material with weight and inertia. Behind these apparent performances lies a multi-pronged iterative methodology combining computational modeling, experimental material science, and tactile craftsmanship. Computational tools allow complex simulations of stress, strain, and failure in ultra-thin shell surfaces before any physical casting, enabling optimization far beyond kind of traditional empirical boundaries. Concurrently, research into the concrete mix development, adjusting particle size distributions, fiber reinforcement types and quantities, admixtures that we just heard about, and curing protocols, all extremely important to make this, ensure that the material can meet these radical formal ambitions without premature failure. Finally, the craft of making, the delicate moments of pouring, supporting, folding, or lifting constitutes a mode of embodied knowledge and feedback, a dialogue between design, intention, and material response that enriches rather than merely confirms the computational models. This cyclical research fabrication dialogue offers a challenge to the conventional architectural workflow, which often accepts material properties as a fixed given aspect of products and systems rather than variables to be interrogated or recalibrated. In the Floating Risolith Island project, we interrogated the long-standing presumption that heaviness is concrete's defining physical characteristic and constraint. By introducing lightweight aggregates, air-entrained technologies, and unconventional casting protocols, we induced buoyancy, enabling concrete elements to float. These buoyant concrete modules serve as experimental platforms for exploring both the material's structural boundaries and its expanded ecological agency. Here, the reimagined concrete raft becomes a living substrate designed to support and accelerate mangrove and oyster restoration efforts in vulnerable coastal ecologies. This proposition challenges the traditional notion of concrete solely as an inert, static, and often environmentally destructive material, repositioning it as a potentially regenerative agent in the climate-adaptive landscapes. Its failure intended to be part of the stabilization of the habitat it provides. This project is situated within a wider ethical and ecological context. Concrete production, as we also heard before, currently accounts for approximately 8% of global anthropogenic carbon dioxide emissions, predominantly from the actual cement manufacture. That's also the reason why there's so much research going on into replacing actually the cement component. These designs and engineering of next generation concretes offer opportunities to mitigate these impacts. The Floating Island project tests material innovations that defy weight and mass conventions and offers practical, environmentally attuned infrastructure for ecological restoration. By becoming part of fragile water edge system, these novel materials may help to reestablish lost mangrove forests and foster resilience against storm surges, increase habitat complexity, and provide water purification processes, turning a traditional problematic material potentially into an ecological ally. After an initial prototype was built for an exhibition in the harbor of Cartagena, which you just saw on the slide before, in Colombia, the latest iteration of the prototypes was developed at a much, much smaller scale, more humble, but with higher technical and environmental resolution. We developed this together with the Smith Group Coastal Engineering and the municipality of Cocoa Beach, who actually reached out to us and wanted us to work together with them to investigate the possibilities of these systems. And they were tested together with local marine biology researchers to see in what way the concrete could be a good substrate for oyster growth. You see some of these testings on the very left. And we installed a series of small prototypes that were pre-spawned for the oyster growth and tested for mangrove development. The third and most current experiments, Thixoform, explores folding not only as a structural strategy, such as folding is typically used in concrete, for example, in Felix Candela's projects, or as we saw yesterday, with Michael Fisak's incredible project that Iker talked about, but as a fabrication process in itself. Folding increases the structural strength and stability without increased mass in various materials like paper, metals, or fabrics, anything basically that you can fold. However, in concrete, folding has historically been more simulacral than literal, cast into static molds designed to give the appearance of kind of folds without the material itself undergoing actual folding deformations. Thixoform, in contrast, use innovations in concrete mixed flow deformation properties, particularly, and that's why it's called Thixoform, thixotropic, or the time and touch dependent behavior of the mix that allow a literal folding during the curing process of the concrete. This approach broadens both formal repertoire and construction economy. In a kind of folding playbook, we documented a whole series of experiments that explored how this fabrication method might cultivate mass reduction, simplify prefabrication workflows, and facilitate disassembly or reuse. Institutional constraints, such as building codes, long a bottleneck to experiment-driven innovations, as we also just heard, are gradually evolving. Newly emergent standards covering fiber-reinforced systems like carbon fiber-reinforced polymer, CFRPs, or steel fiber-reinforced concrete, SFRCs, and revised cover and durability requirements become instrumental for legitimizing these advanced concrete applications. From these experiments, I want to showcase two a little bit in more depth. A first one that explored robotics at the Autodesk Build Space in Boston, and a second one that we are actually at the very moment working on that builds upon the work that we did at Autodesk and is striving to develop a Eurocode compliant precast structural system for a very, very small carport structure. So at the Autodesk Build Space, the folding was realized through the use of large-scale robotic arms, allowing for the needed amount of payload to lift the material. So we kind of required a very large robot. A key aspect of the cast is the relationship between the curing curve and the speed and orientation of the arm movement. That has to be finely calibrated so that it wouldn't slump, guaranteeing for a smooth transition from unfolded surface to three-dimensional casts without slumping of the mix in the formwork. The intent is that the resulting elements can be assembled into complex spatial configurations. The first prototypes demonstrated the technique's feasibility, both in terms of process as well as the precision of the pieces themselves, allowing for consistent output and concise assembly. Based on these initial studies, the aim was then to develop a sort of robotically folded concrete block system that interlocks with a uniform pattern, providing a friction-locked connection between the blocks. We tested the system through the design of a small-scale pavilion. For that, we developed a script that takes any volume and translates it into the information needed to fabricate the pieces, automatically splitting it up into the needed amount of blocks and providing the unfolded geometry for the casting process itself. So you see up there's the script, so you can take any kind of closed polyform into polysurface into Rhino, and then you get automatically the kind of geometry, and it divides it up so that the heights of the modules coincide with the maximum length of the formwork, which then of course is again a function of the payload of the robot. This is cardboard. So due to the COVID pandemic, the work at the build space, we had to stop working there. But at least we were able to use the time during the pandemic to build this cardboard prototype. Still hurts a little bit. At least this prototype kind of was similar to a theater ghost, like occupying the atrium of our school during kind of the kind of quietest time during the pandemic. Building upon the knowledge and experiences we made at the building space, we are currently working towards a kind of industrialization idea for Thixoform. The goal hereby is not to design a completely new fabrication process, so in that sense perhaps slightly different than 3D printing, but to insert it into the already existing precast plant workflow. So on the left, there's some kind of first initial ideas of these kind of machines that we imagine that could be built to fold the elements, and on the right you see actual precast formwork. This is a formwork that closes up for a rather complex concrete frame for a gym in Switzerland. As a catalyst, we are using a request for the design of a solar roof canopy that we had. For us, this is ideal since the scale is rather small, but it requires serial production, code compliance for multiple locations, not just for one, ease of assembly, and possible reassembly, as well as integration of a minimal amount of climate and technical installations considerations. But it was also very important to us that the process, like in the robotic folding project, would allow for formal flexibility, attempting to work towards the integration of digital to physical workflow. While what you see here is a very early model to conceptualize this approach, we decided that we, for now, really focus on the development of the technical aspects of the fabrication process of the elements itself, with the intent to revisit this way of thinking about the relationship between digital and physical workflow once we know exactly the parameters that are given by the fabrication process. So with the aim to keep it as broad as possible. The prototype is then intended just for one car. The structure is based on 2 columns that support a beam that spans 11 feet and supports 3 cantilever joists, about 19 feet in overall length, with the larger cantilever measuring about 12 feet. So this, compared to the work that was shown before, is like, very, very small. The elements are intended to be assembled with typical rigging and joint and bearing pad components that are standardly used in the precast industry. The major challenges are to create a fabrication process that increases the amount of formal outcomes by inventing formwork that can fold to varying degrees and allows for simultaneous bending in the opposite directions of the fold as well, such as needed for to generate the inclines of the cantilevers. The limiting factor for the thickness is not actually the concrete, but rather rebar coverage, which was reduced by the introduction of the Eurocode. I think this was 2021, the Generation 2 Eurocode, allowing for more slender dimensions and obviously with that also a kind of weight reduction. The engineers that are working on the project are also continuously testing prototypes of the folded elements against their calculations. to build out a kind of more general data set that can be used for future applications. Therefore, testing the structural limits beyond the occurring loads in the carport itself. While the folding provides for a weight reduction, the fabrication method also allows for very easy ways to adjust the forms of the members through cost-effective foam inlays that are independent of the larger reusable formwork. This, for example, enables complex interlocking geometries between the columns and the beams. Another challenge is the requirement for continuous rebar in the tensile zones. By ensuring that they are embedded in the outer edges and creases of the members, and otherwise using fiber reinforcement, we can avoid complex rebar bending that can pose a major planning and labor challenge in traditional prefabrication. We are most currently also looking into an option to use, this is the rebar there, and this was just sent to me yesterday. Most currently, we're also looking into an option to use Carbodure, a carbon fiber laminate, to replace the rebar. This is also made possible through the latest Euro code implemented in 2021. And of course, we are in the process of scaling up the mechanical aspects of the work, allowing to automate the folding process in an effort to control the relationship between mix and formwork movement. Simultaneously, CEMEX is also working on the development of a special coating for the foam inlays that will allow the casts to cast intricate patterns. In this case, an abstraction of the principal stress lines in the joists, the cantilevering joists and the beams, with the intent to reduce material where it structurally is not necessary. And this is a few early prototypes of that, showing the pattern and the reduction of material thickness between the stress lines. So, in conclusion, if the earlier sessions of this conference have rightly focused on what we did and what we are doing, then perhaps the proposition here for the might of doing aims to demonstrate that to do by prototyping, experimenting, and making is itself critical form and research and intervention to shape the future. The speculative, the unfinished, and the provisional are not detours from architectural practice, rather they are a foundational condition for its ongoing renewal and recalibration. As material futures become increasingly negotiated arenas of ecological urgency, technological evolution, and inherited disciplinary knowledge, agencies must be understood not only as what is selected, but also as how those choices are enacted and prototyped, shared, and made accessible to broader architectural and industrial communities. The might here is not some abstract potentiality, but a collective strength grounded in sustained, careful making. We see this work as a contribution to larger discourses of work by others. I'm sure we're going to see an amazing presentation just after me. That is also focused on materiality and uses small-scale prototypes, pavilions, and projects as modes of investigation. As part of this larger endeavor, we believe that reimagining concrete is to reimagine the architectures and ecologies it may responsibly sustain. By attending with rigor and openness to the might of doing, we become curators of futures in concrete culture that are not predetermined, but remain contingent and very much ours to experience and through experience and shape through experimentation. Thank you.
Wonderful. Thank you, Roger. Our third I've lost the cursor somehow. Yeah. Oh, got it. Okay. Our third presenter is Caitlin Mueller. She is Associate Director of the MIT Climate and Sustainability Consortium and Associate Professor at MIT in Architecture and Civil and Environmental Engineering, where she directs the Building Technology Program and leads the Digital Structures Research Group. Her work integrates architecture, structural engineering, and computation to develop innovative, low-carbon, and human-centric building design and fabrication methods. Current projects explore circular construction, structural optimization, and machine learning-driven design. Mueller holds degrees from MIT and Stanford and has authored over 140 peer-reviewed publications. Her awards include the 2021 Acadia Innovative Research Award of Excellence and the 2022 ACSA Diversity Achievement Award. Caitlin.
Thank you. It's so wonderful to be here and spend this quality time talking about a material that I think we all love and also are questioning in today's world. I just want to start quickly by acknowledging the team that has led to most of this work. My research group at MIT is called Digital Structures. We've been around since 2014, and we're a pretty diverse group across people with backgrounds in architecture, structural engineering, computer science, mathematics, and we're united in an interest in buildings and architecture and in developing new ways to design them and build them, mostly aimed at improving sustainability outcomes through harnessing emerging technologies. And I just want to start with a graph that I was certain would have already appeared. So sorry to depress all of you with this reminder, but we're in a climate crisis and the built environment is a major player, which is both a challenge and an opportunity for those of us who work in this area. 42% of global greenhouse gas emissions are attributed to the built environment. A lot of that is operating buildings, but a larger and larger percentage of that is the construction, the embodied carbon associated with the materials we use for construction. And in this particular plot, I really like that it also calls out specifically cement and steel, which are by far the major contributors. And if you add things up, it's about 8% of global greenhouse gases are due to cement use alone. And we're not going to change that by halting construction. We need more construction in the world than we've ever had before. There's an unprecedented need to build because of growing populations, because of urbanization, because of development, which has a really positive impact on people's lives around the world. How can we build in a world? How can we continue to contribute and improve the lives of all of our citizens while somehow tackling this tremendous challenge? There's been a lot of effort by a lot of different groups to start to address this. This is a plot from a group from SCI SC 2050, which is a committee focused on eliminating embodied carbon from construction by 2050. That's a huge challenge. How are we going to go from what we have now to zero? It also shows the commitments from the American Institute of Architects 2030 committee, which is focused on operational carbon. You can see we have a really, really big challenge ahead. A big part of the strategy here is to use more renewables to produce materials. So this kind of green concrete and green steel movement is mostly the idea that architects and engineers can give themselves a break and will just use nuclear energy and other renewables to create materials in the future. There's a lot of reason to like that idea. It allows us to continue to be creative and do whatever we want, but it also shirks a lot of responsibility that we have to this problem, and it's going to be incredibly expensive, and we're incredibly far away from doing this. So what I'm going to argue for today is an alternative, complementary approach that allows us to get to zero by using what we already know how to do today, design and engineering, and the materials that we have, and just really thinking about them through this lens and moving to zero by being better at design. I also want to point out, some people will say the solution to this problem is to just stop using concrete. We should just only use other materials because concrete is such a substantial emitter, as seen from this 8%. But the data doesn't back up that idea. This is some data that the Concrete Leadership Forum, CLF, produced this spring, which is the result of a large-scale data set, well, not that large scale, several hundred buildings that they were able to collect and plot the embodied carbon. That's what's along the x-axis per square foot of floor area or per meter squared of floor area. And here they're spreading it out across the 3 different materials with the attempt to say, is one material more carbon emitting than the other? I think this plot says no. The other thing that I think is really dramatic is that within the materials there is a tremendous variation. There's an 8 times variation in terms of how each of these materials intensifies its carbon impact. Again, my argument is that that is due to a question of design. It's which materials we use and how we use them, how we organize them in space to create enclosure and to carry structural load. One especially egregious example of this that many of you may have seen before was produced by some of my colleagues, John Oxendorf and Catherine DeWolf. About 10 years ago, they did a study of the embodied carbon in Olympic stadia. We have Beijing on the left from 2008 and London from 2012, 4 years later. They're both made out of the same material, steel. And yet the London Olympic Stadium is just 1/14 the embodied carbon per seat compared to Beijing. So there's a 14x differential in performance, not 14%, 14x. It's not just a question of a material, it's a question again of how the materials are organized in space. And this reveals both a challenge to designing in a way that is totally indifferent to our carbon impact, but also a huge opportunity that we designers can play a really leading role. In a lot of my work, I try to do this through a computational approach because I find that having access to this information early in the design is really empowering to allow us to make good decisions. I use something called the design space. That's this plot here, for example, for this truss. If I change the geometry of the truss, if I make it shallower or deeper or narrower or wider, the total amount of material that I need changes. That's this relationship between geometry and structural efficiency. I can use antique algorithms from the 1950s to find the very optimal solutions to these problems. These algorithms have been on the shelf for a long time, but have really rarely been used to design buildings because they're fairly inflexible. Architecture is not just about weight minimization, but it's about this holistic range of goals. But the design space also offers the opportunity for us to explore that. If we kind of zoom back out and relax our goals or incorporate additional goals, we can use this technology, this computational approach, to find ways to both save a lot of material and discover new forms. This is not a new idea. This was, people have been thinking about this for centuries. This is an illustration that Galileo made in 1638 from Two New Sciences, where he was curious about this wooden beam. How big does this wooden beam really need to be to carry the load of that rock at the end of it? Well, we certainly know that we could make that rectangle bigger or smaller, right? We could adjust its overall dimensions, but could I start to carve away material in a nonlinear way along its length to reduce its mass? Does anyone think the answer is yes? Yeah, the answer is definitely yes. We can carve away a lot of material. You may have heard that a good structure should follow the moment diagram, right? So you remember a moment diagram for this problem is just a linear solution. It turns out, because of the complexity of beam theory, it's not quite a linear pizza slice, but it's a square root function, essentially, that is the optimal shape. That allows us to save 33% of material. So we've known this for hundreds of years, that there's this relationship between shape and structural performance, but we have stopped leveraging it, I think, because of an understanding of construction economics. And yet, if we start to think about this again, especially in concrete, the opportunity is immense. Concrete is especially amazing of a material because unlike that wooden beam where I have to cut off a third of it and then figure out what to do with that extra piece, we can be super precise about concrete and really use only what we need because of its plasticity and fluidity. This is kind of a spoiler of the research I'm going to show, but what we've seen is if we carve away structurally unnecessary concrete and ubiquitous elements like floors, we can save more than 50%. We can save 60, 70, 80% of total embodied carbon due to both the cement and the reinforcing steel. By making it more lightweight, we can use less reinforcement, which has really substantial effects and could be used in many very typical buildings around the world, and it has been. This is another historical example from Spain. People love this type of thing, right? There's this sense that, oh, no one's going to want to have this kind of exposed complex structure, but this is a feature in this historic building that was turned into a high-end residential project where this peculiar ceiling, as the interior designers wrote about it, was really the key feature in the space. We're also not arguing for necessarily a single solution. Different types of contexts will have different available formwork technologies, will have different kinds of accessibility to labor. And so our argument is that we can kind of have this menu of solutions that we can find where we can integrate computationally what's possible to make, what materials are available, and then we can figure out how much we can save. This is a plot going kind of from simple to more complex. Even a flat slab can be optimized and often is not, so exactly how deep do I need it, exactly how much rebar do I need, which strength should I use, those are still sometimes open questions. If we start to make it a rib slab, that's kind of the best bang for your buck. Ribs are really, really good, but we can continue to carve more and more away as we apply the Galileo techniques. And the way that we've been doing this in our research is by developing what's called a constrained optimization tool, which essentially parameterizes the outer boundary of the concrete and then runs structural analysis based on ACI building code at sections along the length to check shear and flexure, to make sure that capacity exceeds demand, check total deflections, et cetera. So all of this meets building code today, uses today's building materials, and yet can result in substantial savings. How do we build these things once we design them? We've been experimenting with that with a variety of different partners for quite some time now. This was a prototype we built with partners in India, where we had original funding to do this work to look at reducing the cost of construction of concrete housing in India. We worked with a group that had a lot of expertise in manufacturing, and when we first showed them our beam and we said, can you make this beam? These are T-beams that get arrayed horizontally to create a floor. They said, sure, no problem. And we said, well, at MIT, we've been CNCing milling foam to make the formwork. Do you think that's a good idea? And they said, no, foam is illegal in India because of its environmental intensity. We said, okay, that's fine. How else would you make it? And they said, no problem. We'll just get a giant block of solid steel and we'll mill out all the steel. And we were like, that sounds also very expensive, even though it could be used many times still, because they were coming from mechanical engineering where they're making smaller things. So finally we said, well, how else do you build concrete in India? I see so much complex concrete. They said, oh no, we just use steel and we just laser cut it and cold bend it and weld it together and make forms. And we said, okay, perfect, let's just do that. The only problem was that our original design had types of double curvature that couldn't be achieved with cold bending steel and single curvature. But our computational approach allowed us to, actually Mohammed Ismail, who led this work, remote desktoped into his computer back in the US from Delhi and re-parameterized the problem so it only had single curvature, and like half an hour later came up with a new design, was slightly heavier, not too much heavier though, and it could be built using this amazing technique so that we were able to build a 5-meter prototype and test it. We've since kind of developed a similar set of approaches using using building code, using what we already know is possible, not trying to reinvent the mechanics, but use what's allowed to develop sort of full building system modeling techniques. We use books like this that when I was a structural engineer I used every day, which make it a lot easier to design structures manually, but also can be implemented into algorithms to explore things at the full building scale. This is a kind of very high fidelity full building frame model that we've developed for kind of early stage design iteration. And one of the things that we're trying to show here is if we only change the material, the amount of savings we can find is very small. But if we start to integrate these additional findings like lightweight concrete floors, reducing the column span, that's a huge one, changing the types of foundations we use, again, we can get close to zero through design alone. The other thing we've been able to study with this type of approach is comparing across different material systems for buildings. This is always very controversial because all of the stakeholders from the different materials want to be very careful to make sure that I've represented all of them fairly. And so this is our attempt at a peer-reviewed, very fair apples-to-apples comparison of the same building rendered in different materials with different design decisions. The reason that we did this was to convince policymakers that they should enable designers to be part of the solution to the climate crisis and not alone depend on materials and alternative energy sources. And so what we were trying to show here on the left is a reinforced concrete system with a two-way flat slab on a frame structure, and as we move to the right, we have kind of steel frame structures, we have different mass timber structures, we look at reusing elements. There's an act called the Buy Clean Act that the Biden administration recently passed to address embodied carbon through material substitution, which does have an impact, but the impact is, again, fairly modest. So if we only change the material but nothing else about the building, we can save 16%. That's going to be really hard for us to get all the way to zero. But if we use a combination of design techniques, we use a better material, yes, but we also reduce the column spacing. We also carve away unnecessary material from floors to make them lighter. The savings, again, can be really, really substantial, and this is at the full building scale, so it's also accounting for the lightweight, the foundations can become lighter, there's a sort of knock-on effect. We also see that if we set a very ambitious target, all material systems can potentially get there. So if we're aggressive and ambitious about what we can do in the carbon space, not only that's not going to create winners and losers, it's going to create innovation and allow many different material systems to find ways to be cost-effective and innovative within their spaces. So that's what we've been arguing for, that we should really empower the design community to design towards goals rather than to prescribe solutions that actually aren't very effective. There's also more that we can do with concrete in addition to sort of just using less of it. We can also ask it to do more for us. When I was an architecture student, I remember learning about concrete and loving it. I've loved it my whole life, but learning, the great thing about concrete is it has all this thermal mass, and that's like really, really good for the way the building behaves. What I've learned since, especially from colleagues who work in building energy and building physics, is that that can be true, but actually the amount of concrete you need to activate thermal mass for a diurnal temperature kind of balancing is really thin. The thermal penetration depth is like only a few centimeters. So we said, well, could we sort of think about carving away all this material in a way that also has thermal benefits and actually like gives us more thermal mass effect without more mass? And so that's what we did in this research project, where we looked at whether we could optimize the shape of the concrete to maximize the heat transfer between the space and the floor system. Here we have activated hydronic systems providing cooling to cool the space. And there's an interaction between the shape and the material properties that we were interested in to try to basically develop alternatives to air conditioning. We developed a computational system in which we studied kind of geometry, its relation to thermal behavior and structural behavior, and then sort of full building impacts. We started with this multi-objective approach in which we were studying the trade-off between embodied carbon minimization using less material and this thermal factor. And we did find this Pareto front, the red dots basically show there is a little bit of a trade-off, but all of these designs do better than the equivalent flat slab. So by carving away material, we expose more thermal opportunity and reduce our mass. We studied the thermal behavior more precisely using conjugate heat transfer simulations. This is kind of just a fun image of the model where we are able to study the dynamic behavior of the interaction of the space and the concrete over a 24-hour period, and then start to turn that into full building impacts where this is showing cooling capacity, so basically, could we start to achieve the requirements for different functions of spaces, and then also look at building energy use and carbon emissions over time. And again, what we found was the shaping system can reduce upfront carbon and reduce long-term carbon through operational energy savings at fairly large percentages, especially compared to a flat slab with an air conditioning system. We've started to integrate these tools and teach them to our students. So Mohammed Ismail built this tool that wraps up this concrete optimization software that I described into something that's intended to be accessible so that you can optimize any structure you want. And then we also asked a machine learning algorithm to take a lot of that data and see if it could learn what the optimal solutions were to produce results much more quickly. So basically, this is a neural network in which we trained it with a lot of synthetic data from our optimization tool and asked it, if I tell you my span, my maximum depth, my material properties, can you give me the shape of the efficient structure instantly? Because our optimization tool does take several minutes or I don't know, half an hour to run. And we were able to do that, and the outcome is basically allowing us to compare results really, really instantaneously. So it really becomes a design modeling tool rather than an engineering tool where you're studying different configurations, and I'll just get to the part where we're kind of in real time. This was also during COVID, so we were like, what can we do with with augmented reality? So here we're in like a VR headset, and we're imagining an architect or even a client in a space and starting to play with this idea of these articulated joisted slabs and seeing both what they look like and what their carbon impact is in real time. Once we got out of COVID, we wanted to get back into the real world, so we started building and testing a lot more of these systems. We got to do this project in Mexico City for the 2022, I guess. Anyway, for the Mextropoli of Architecture Festival, where we wanted to demonstrate a prototype for affordable housing. The concrete beams are precast with a fiberglass formwork that we created with a local partner in Mexico who specialized in ornamental concrete. For a long time, it was very hard for us to find partners who could make more complex forms, and we learned that there's this whole world of people who do architectural ornament who are actually really good at making structural concrete formwork. This is a system that is a riff on a very traditional Latin American construction system for floors called Vigueta y Bovedilla, 5 minutes left, which is block and beam system with precast concrete elements and some kind of temporary filler that gets a topping slab cast on to lock it all together. The ingenuity of the system is that it's very lightweight and you don't need any heavy equipment to move any of the parts together. We decided to explore whether optimization could make it even more efficient, and we were able to save 50% of the carbon compared to a typical system. The rest of this is compressed earth, stabilized block walls that our partner had developed, and the bovedillas are made out of a fired ceramic clay. They couldn't be made with traditional means because each one was different due to the shaped concrete, so we worked with a local partner, a local ceramics factory and a local partner to robotically extrude these different clay elements and fire them so that they could fit perfectly onto these shaped beams. And here's the extrusion process that our partners carried out. And so we were able to kind of create this mixed material system that was dry fit together and worked on site. The students who developed this project created a company called Forma Systems, where they're now trying to commercialize this idea. So if anyone wants to try this on a real project, this company exists and is eager to help you with it. Their primary business strategy right now is trying to develop software for precast manufacturers, but if anyone else wants to do this, they're very eager. They've also experimented with other ways to use additive manufacturing. This is printed soil formwork that has no cement in it so that the formwork can be reused over and over and over, which allows us to make large-scale shape-optimized things very quickly and easily. The rebar is by far the slowest part of this process. Since I only have a few minutes, I'll just go quickly. We've still been doing more with steel. This is with the University of Arkansas with Emily Baker and Edmund Harris, who are amazing digital fabrication and geometers, who figured out a really smart and inexpensive way to make cold bent steel formwork, with Fishman making this mold, where we did another large-scale test at the University of Arkansas. We also found out that this formwork is less expensive than traditional formwork. This was a partnership with a commercial formwork company, so I really think cost is no longer, is becoming eliminated. We're continuing to do this in other parts of the world. This is Mohammed Ismail's work on a pavilion in Kenya. Here's Forma Systems winning a climate and energy prize at MIT. They beat out people working on nuclear reactors to work on concrete, so I'm super proud of them. Last quick project I want to show is another idea using less material, but also thinking about how to use it over and over and over again. This is a project called Pixel Frame that my group developed with Holston and the MIT Climate and Sustainability Consortium. It's a precast, post-tensioned, separable and reassemblable not reinforced concrete system to make structural frames for buildings. There's no internal reinforcement, so all of the parts remain just concrete with a little bit of fiber reinforcement. And the idea is there's a single unit, the pixel, that's made at different strengths and can be assembled into different components to make beams, columns, and frames. It's meant to be this kit of parts that is tracked and kept track of so you can use it over and over and over. And there's a lot of emphasis here on beauty and value and aesthetics. We're trying to turn this from something people think of as garbage to something that's jewelry, where all of these parts are really beautiful and desirable and inspire people to want to keep track of them and keep their inventories of them, the same way that they do with higher value things like electronics today. These are really high-tech pieces of technology that are assets to care for and treasure. At least that's what we're trying to say here. Behind this is a complex computational system that helps us keep track and allocate things. And the idea, again, is these pixels circulate between industrial settings to cultural settings to, this is an adaptive reuse proposal. The very last thing, another project kind of in the same vein, but thinking about waste material, looks at concrete rubble in the same way and says, can I take concrete rubble that's literally garbage? This was from a project in Bahrain where there was a lot of mid-century concrete projects being taken down, and use the heterogeneity of the rubble productively. Here, post-tensioned elements are put together to string as beads to make compressive elements on trusses. I love trusses. I love optimizing trusses. But normally in a truss, you have variation of forces, and it's really hard to materialize that to make every element different. But here that comes for free from the variability of the material. So where we need thicker material, we use larger pieces. And we have this algorithmic matching process that enables that. And Latifa Al-Kayat, who's led this work, is really also kind of pursuing this from a representation and kind of cultural perspective, where these are some of her Instagram posts where she's showing this. She's working with local labor in Bahrain to start assembling these types of pieces and really promoting this transformation of concrete garbage to concrete jewelry that I think is really exciting. So to conclude, I think we really need to focus on decarbonization. I think concrete is a really important lever, not to eliminate, but to rethink. And there's a lot of creative opportunity here for us to contribute. Thank you very much.
Wonderful. Thank you, Caitlin. Our final oops. Sorry. Where's Ted's? Yeah. Oh, there we go. Okay. Got it. Yeah. Thanks. Sorry about that. Our final speaker today and for the conference is Ted Fishman. He is an award-winning journalist. In his international bestseller, China, Inc., he describes the global effects of China's emergence as a world power. Fishman's book, Shock of Gray, explores how the aging of the world's population drives globalization and changes our most important relationships. His writing appears in many prominent publications, including the New York Times Magazine, Harper's, Fast Company, National Geographic, New City, and Chicago Magazine. And he's currently working on a book for W.W. Norton, the subject of which you will be surprised to learn is concrete.
Hi, everyone. So glad to be here. One time I was giving a talk about my book, Shock of Gray. I was the last speaker at a huge conference, there were 10,000 people there, and they advertised it as being about shades of gray. So the room was packed. It was the last meeting of this whole conference. People came with their roller bags, and as I started talking about the aging demographic of the world instead about sex with mysterious men and women, people started walking out with their roller bags. So I'm so glad I don't see any roller bags. First of all, thank you for having me. This is an honor to be here. I'm an odd duck in this very knowledgeable and technically expert group. I know many of you. I've learned from many of you. I've written about several of you. And so much of this conference was new to me, and I'm just delighted. And I love my panel. It's been fabulous so far. Thanks, everyone. I'm going to show very quickly a series of slides. I'm not going to talk through them. I just want you to look at them and think about what your first thought is when you see them. There's a bunch of them, so I'm going to go fast. I think some of these locales will be familiar to many of you. All right, there we go. All right, keep those in mind. My topic is concrete in the future, and I thought I would divide the future up in different kinds of futures. There are so many different futures possible with concrete. I feel like the last panel in the early part of my panel totally stole my act. But I'm going to work to put that all in context. If you hear anything that sticks in your craw, please call me on it. I'm going to take issue with some of the things that were said here in a polite, respectful, and I have to say, very appreciative way. I'm so grateful to have those issues come up. You know, one of the things concrete does is it creates the future for everything. It creates the future for us as individuals, for our communities, for our country, for our planet. But it does this by drawing on the deep, deep, deep past. You all know that the Earth has given us the raw materials for concrete, and it's done it through hundreds of millions of years of processes. But most of the raw material comes from living things. Nearly all of the limestone on the planet comes from tiny creatures, which created the raw material that became limestone, which is the chief store of carbon on our planet. And you know, there's a lot of discussion in the sustainability kind of realm about using more natural materials. It's hard to imagine a more natural material than concrete. It comes from the most fecund period of life on the planet. And it is so tied into the carbon cycle of the planet that, you know, one of the big challenges is how do we get this natural material back in line with the natural carbon cycle of the planet. And in that way, it affects the futures of us all, you know, uncategorically. But it also is a very emotional material. One of the professors at the Concrete Sustainability Hub said something to me that has stuck with me, as Franz Holm, and it was that concrete arrives in the United States without an ideology. But in the rest of the world, it carries a strong ideology. It is really the stuff of politics, of dreams, of national aspiration. I have a collection at home of postage stamps with cement plants on them. You know, these trumpet the importance of cement to the nations that issued the stamps. I have a 1924 U.S. postage stamp, which is commemorating the 100th anniversary of the patent on Portland cement. I have a 1952 Polish stamp, which shows very comrade-looking workers with their huge, huge, flag-worthy tools next to, a giant kiln turning some giant gear that I can't recognize. In the communist bloc, concrete was the people's material. Shostakovich wrote a comic patriotic operetta about a couple that was moving into a new concrete apartment block in the Khrushchev era. It was so important to the state. A South Korean stamp from 1972 has a dramatic one-point perspective, it's really pretty, of a vertical kiln in a calcinator prepping the country not for communism, but for its very, very capitalist anti-communist future. And a Thai stamp, really interesting, shows this, what at the time was an ultra-modern cement plant on a riverfront, lined on the river by sampans that were carrying the cement to places throughout the country. This is where modernism meets traditionalism and carries it forward. Concrete and cement are very, very potent emotional materials in our aspirations. And the reason is that for most of its history, and by and large, for the people who make it and use it, it is highly useful, and it promotes the things that we want in life. Concrete is connected to almost every realm of human betterment for the last 120 years. Public health, transportation, defense and security, telecom, infocom. It is the material that networks all other materials. And as I look, I did this very deep dive into human demographics for my last book, and it seemed to me over and over again that the most powerful tool for public health is concrete and the things that concrete networks. It's probably done more than anything else to extend the human life by almost 40 years. So when we are thinking about the dangers of concrete, I think one thing we have to keep in mind is who among us or what geographies in the world would we ask to trade back those 40 years of extended life if they didn't have to muddle through climate change? You know, climate change is a danger to us all, but we also like living twice as long. And we're not going to give that up, and that's part of why concrete is in our future to stay. Concrete tends to go up in its use as economies grow. And you know, this is just easy to figure out as places urbanize, build their infrastructure and so on. Of course they're going to use more concrete. China at its peak in its post-market, in its market era, used as much, if I have the years right, used as much concrete from 2019 to 2021 as the United States used in the entire 20th century. Some of you might know that statistic already. It's pretty widely broadcast. And, you know, countries use vast amounts of this material. This might have been said at the very beginning of the conference, but it sticks with me, which is that the whole world produces in excess of 30 billion tons of concrete every year. 30 billion. That's about 4 tons per person. My mother, who lives at 340 East Randolph here in Chicago, is almost 100 years old. That means, like, per capita, there's going to be 400 tons of concrete for my mother. That's like 10 ready-mix trucks driving up to her front desk. You know, imagine the Uber Eats people delivered concrete for a lifetime. It's like, Mrs. Fishman, your 10 trucks are here. You know, the statistics on like the gross use of concrete since, you know, the beginning of its mass industrialization are kind of all over the place. The most outlandish one, I don't think it's true, but I did see it, was that the urban world weighs something like 90 trillion tons, and 80% of that is concrete, which would mean there's 6,000 tons of concrete per person in the world. You know, if you add up the cumulative amount of it. I think the message here is that despite all the modern things that concrete gives us, despite all the things it networks, we are still in the Stone Age. A geologist in Wisconsin said, "Ted, we are in the Stone Age. We will always be in the Stone Age." There's no escaping this material. It's 80% of what human beings make. Concrete is 80% of what human beings make. Does it translate into prosperity for countries? Well, I know a lot of you have been to Switzerland and have studied concrete in Switzerland, but it's also worth considering how concrete made Switzerland. You know, when Switzerland was the poorest country in Europe, it decided to build a tunnel that would connect northern Europe to southern Europe. It was the longest tunnel in the world at the time, the Gotthard Tunnel. And in order to do that, they needed to create a special purpose financial vehicle to build the tunnel and to finance the cement industry that would take advantage of the material they took out of the mountain and turned into cement and concrete. And that special purposes financial vehicle became Credit Suisse. So concrete gave Switzerland its banking industry, Switzerland's financial resources. They then gave Switzerland its industrial infrastructure. And you know, Switzerland is one of the wealthiest places on the world, and it is obsessive about concrete. It's one of the places you go if you want to see beautiful concrete, because the country and the Swiss people know how much it means to them. More recently, they know the dangers that are brought by climate change, and they're also pushing for change with that. The Midwest exists largely because of the industrial Midwest, the industrialized Midwest, exists largely because of our access to rock and waterways. Before my mother was born, a few years before, like a decade or two before my mother was born, there were 500 rock quarries in the Chicago area. When she was born, there were 100 rock quarries in the area. There aren't any anymore. There's giant quarries in other places. But it was, so central to the development of the Great Lakes region and what became, for many, many decades, the most industrialized and powerful industrial region of the world. You might have seen in the slide, some of you might have recognized some of the scenes in South America and Brazil and in Colombia. One of my trips to Colombia, I spent time in Medellin, which is an amazing story of urban renewal. I mean, it's backsliding a bit now, but it's still amazing. And one of the things that I wanted to do was to see how urban planning with the use of concrete transformed that city from really one of the world's most dangerous places to one of the world's very treasured places. And I was talking to, actually many of the people in this room may know him, Alejandro Echeverria, the urban planner. And he said, Ted, Colombians don't really build with concrete. They build with brick. And they like the earthen color of the red brick. And then he called me a day later. He goes, you know what? I'm going to revise my remarks because the brick is connected with concrete. The new buildings in Medellin are all concrete. But even if you go into these barrios, which is the Colombian equivalent of a favela, you should look at the stairs. And I had many pictures of stairs that I scrolled through. He said, before people even put their houses together with fond materials, they get their neighbors together to build stairs. And they invest together in bag cement, and they pool what kind of found aggregate they can get, and they start building stairs so that they can build houses up these hills. And then the stairs become the networks for the community. And there are stairs everywhere, and there are concrete stairs everywhere, and people take good care of them. So I was looking at one of these staired neighborhoods, and in Medellin, they have these very interesting social centers, which are the former water tanks for the town. They used to be surrounded by barbed wire. They were the dangerous places. They were identified as the least hospitable places by satellite because they were pitch black on a satellite image. And the city converted them into community centers, health clinics, and parks and fountains, and so on. And at one of these, there's this old kind of machine house just on the hill just above it. And I said, what's that? And they go, oh, that's the first power station of Colombia. And I said, oh, well, let's go take a look. And you go into this, I think it's from the 1880s, you go into it, and there's concrete holding up the building and creating a floor for these very early English turbines. And I said, where did the cement for the columns and for the building come from? They said, well, at that time it had to be imported from England. But it gave the city power. And when it gave the city power, it gave the city industry. So the elites in the city financed the building. They provided power. They controlled the financial infrastructure, the power infrastructure, then the industrial infrastructure, because they had the keys to the kingdom in that way too, and Medellin became the industrial powerhouse of Colombia. And that's kind of the story all over the world. If you want to start your country on the way towards kind of a modern version, post-Ford version of industrialization and prosperity, you begin with power. Maybe you build a dam. You get the power, you have the financial infrastructure, you have the industrial infrastructure, and incidentally, you create an oligarchic class, which is part of the picture, and cement is almost always connected to the oligarchic class. There were many pictures in there of we've seen a lot of great buildings over the last 2 days, fantastic buildings. I will say that one thing struck me about many of the buildings we saw is that they could be the star buildings in movies about utopian futures, but with different soundtracks, they could be the star buildings in dystopian futures too. Because what's starkly beautiful is also stark. And I think when a lot of us think about concrete design, we think about that. But for most of the world, concrete is something very, very different. So for the families that I met in Medellin, they moved to these gigantic, so-called slum communities for different reasons than people move in other parts of even Latin America. In Brazil, they might come to the favelas from the countryside for economic opportunity. In Colombia, they come because they're traumatized. They flee enormous violence. Almost everyone I talk to in those neighborhoods had somebody in their family killed. And then they come and little by little, they build a house. They build a house in an unregulated area, first with sticks and stones and vinyl billboards, and then they buy, with their first disposable income, they buy a bag of cement. And then as the women wash clothes in the river, they collect the stones from the clothes they wash, and over the next 3, 4, 5, 10 years, they build a house. And that house becomes a member of their family. It's built by their brothers and sisters. It gives them security. It's their hedge against inflation because their money is now in something physical that keeps its value. And it is so important for them. Their word for concrete is the same word as just the word for material. And it's part of their deep aspiration. And it was interesting talking to them. They would invite me in for coffee. We talk, they tell me about their house for about 20 minutes, and then almost 2-1, somebody in the family would start crying because the house meant so much to them, and it was so transformative for them. And that's where concrete is going. So you wonder, why in addition to that? Well, one reason is, I mentioned public health and concrete. If you take those simple houses and they transform over time, they can also provide for great benefits to the family health. The Mexican government did a program where they provided concrete floors to 100,000 poor families in neighborhoods where the floors were mostly dirt floors. And a miracle happened. The death among children from intestinal disease, which is the #1 killer, declined rapidly. The cognitive ability of children aged 3 and 4 went up by 9 or 10% when measured by their language. The missed days of school and the missed days of the parents from work went way down, and the family prospered. Just because of a concrete floor. There was no toilet, there was no sink, there was no kitchen, just because of the concrete floor. And I saw this in Colombia too. And there was nothing you could do better for these families than give them a concrete floor. What the Mexicans found that it performed for the betterment of the families better than nutritional supplements, better than nutritional programs, better than other public health programs. It's pretty incredible. So I wanted to say another thing about, so we've gone from countries to the individuals. Let's get big now and talk about the world. We've heard a fair amount, and there's much, much more about sustainable approaches, and they're really enlightening, and I'm leaving this conference feeling really excited about learning more about them. I hope you'll indulge me. But concrete is the world's most used industrial product by far. It does have an onerous carbon footprint. But it's also one of the very few things that has the scale to do more than solve its own carbon problem. It has the scale to solve bigger problems. Ben talked about a company that I've written about, Prometheus. Prometheus switches the equation on carbon emissions from one where cement emits carbon to one where cement is excreted from a cyanobacteria, sometimes called pond scum, or algae, which it's not, and it absorbs carbon dioxide. So if a material like that were used en masse, it could absorb the emissions from other industries. There's some challenges for it. It needs a lot of land to grow in and to operate in. By my calculation, Ben, it needs more land to grow in, or at least more land to grow in than all of the grains in the world. But we have a lot of empty shopping malls in the US. We could put it in there. There's a company called Blue Planet, which makes aggregate out of captured carbon. If their calculations are right, this could start sucking up gigatons of carbon dioxide far in excess to cement and concrete's emissions. And once you start talking about technologies like that, that reach beyond the real but narrower problem of sustainability of that material, and you use a material at scale to solve sustainability of the world, we have a reason to use more and more concrete, not to use less. And as Caitlin said, the world's going to need a lot more. There's going to be 3 billion more people before world population evens out. They're going to want houses. They're going to need houses. They need to get those concrete floors. And if we can enlist concrete as an ally in all of these problems, then you'll get the low-income housing, you'll get the concrete floors, and you'll get a much better life and human betterment for all of us. Thank you.
Great. Thank you, Ted. And if we could have our panel meet up here around the table. Yeah. That one on? Oh, I've got a, yeah. Thanks to all of you. That was as thought-provoking a panel as I've seen in a long time. And it makes me think about a number of things. I think to try to draw a very broad conclusion, what impresses me most is the kind of agility that the material has in all of your research and experience. That I think about the image of the laboratory, or the kind of very refined algorithms, Caitlin, that you're using, and then to think about a concrete floor in Mexico, or a sack of concrete that is used by a family over a period of years to build a house. And it's the same material, but in these different, it's able to be used in these different contexts that go from jewelry to something that is, clearly handmade and not with no sense probably of the kind of art of concrete, but kind of getting it done and being able to use the labor of the family. And I can't think of another material that would do that, right? Even brick requires a certain skill. So I have a number of kind of provocations that come to mind, but the one that I think comes to mind immediately is years ago a contractor on a bad day on a job site, and they said, the hardest place in the world to build a building is a construction site. Absolutely right. And looking at, Ben, some of your work, and especially the 3D printed house on a hot day when the concrete is clearly not setting as fast as it should, and the kind of, in some ways, very beautiful, but also, I'm sure, kind of off-putting appearance when it's done in some ways. I would like to ask all of you about the trajectory going forward and the distinction between the concrete that's placed on site, where the problems of climate and of placement and of labor and all of this are really pressing, versus the kind of laboratory or factory production where we can get the fish belly beam shape and we can get the perfect finishes and we can get the kind of ideal strength. The consequences both for how we build and the costs of building, but also the problems of labor and moving so much of the work from a job site where we might be able to employ hundreds of unskilled laborers in ways that are productive to something that is a much more kind of high-tech and therefore more automated, but also less kind of employable process. And just in your own experiences, but also thinking ahead, is this a material that is handcrafted on site still, or is it a material that becomes a much more honed, factory-produced, automated material?
Yeah, well, I can jump in there. it can certainly be both, right? As we've seen, it's interesting because so many contractors that you meet may have started out as concrete contractors, as concrete providers, because the best foundation you typically find is putting concrete in the ground one way or another. And there is that kind of, I'll say, very utilitarian approach of something that is just, how do you meet the earth? Like, what is that first material that is going to found your building, whether it's a concrete pile that's 100 meters in the ground or a big concrete raft. You're always going to have that kind of place for it. I think what we find oftentimes is that prefabrication and precast elements really reduce the waste, and so we can do optimization that will carve away materials as you go, but just being smart about the manufacturing process, even if it's still, I'll say, a dumb shape, can go a long way. And so you'll see contractors out there like O'Rourke, and they're big in the UK and certainly international group, where their goal is to make everything precast for all of those different elements and the value of them. And when you embrace that kind of, I'll say, humble material and concrete and mix it with prefabrication techniques, it really does lend itself to these alternative materials, because you can test it in the factory before it goes. When you're using experimental material in the field, that's where things kind of get dicey, right? You're not sure what you're going to get, versus you got a larger degree of QA/QC. And so when you think about things like the BioBrick and Prometheus, starting with individual units allows you to control that. And so I do see a really a nice synergy between reducing waste in prefabrication, as well as high performance, more sustainable materials that need a more watchful eye. But I'm cognizant that we'll probably never get away from that first material that has to touch the ground, which is just going to be a hardworking utilitarian, poured on-site concrete.
I think there are ways to achieve quality and beauty that are diverse. Like, I don't think it has to be always about the smoothness of the finish or the crispness of the edges. I remember being kind of surprised that in school I was taught about all of these brutalist masterpieces, and then in working as a structural engineer, contractors would act like architecturally exposed concrete is like never done and is incredibly complicated, and yet then of course that's how like most people's houses around the world are built. And so I think, I think sometimes we just have to be a little bit more flexible in our mindset of what is beautiful, what we're willing to accept. I think like the examples that Iker showed with the experiments with the form, like there's just so many different ways that we can achieve beauty that don't require a precision, right? Probably, I don't know if he's still here, but all of those flexible forms, probably each one was a little different. Mm-hmm. And that's okay, right? And it still looked amazing, and it was beautiful, and it was controlled in a less controlled way. I think there's, we have become so narrow because of just specialization and advancement that I think that holds us back sometimes. And if we loosen our expectations or embrace, as Julie was saying, like embrace kind of unexpected outcomes, that can be super productive.
Three things come to mind. One is that when productivity goes up in construction, it tends not to reduce the construction labor force, it tends to increase it, because the number of projects goes up. So there was this example that we talked about earlier. When ready-mix first came into the Chicago market, Material Services worked really hard to convince the unions that it was in their interest. Well, the masons were against it, and so were a lot of other skilled unions. But finally, the case was made that the productivity would cause a building boom, and it happened. And then union membership went up threefold. I think that's incredible. So that's one thing. The other thing is there's a constraint in factory fabrication, which is the time constraint. Almost all of the prefab solutions that I visit that have new formulas for cement or concrete require long cure times in factories. The factories want to turn the material around really fast. And then the last thing I would say is we shouldn't just focus on new construction. The most sustainable strategy is to preserve and restore. Well, the United States and the rest of the world has an enormous inventory of things that need fixed. You can't fix them with the prefab things. And if we're going to be serious about sustainability and serious about saving our cities from crumbling, we're going to need more skilled workers who are good at that.
Yeah, I was just wondering also what, to be careful to say, well, there's skilled laborers and there's unskilled laborers. I think it's a gradient. The idea, I think, should be to lift people more into the skilled labor. So I think there's also a potential to devalue the labor by actually not requiring a certain amount of knowledge, so that makes the labor valuable. It's one thing in actually, it's a funny conversation in actually a precast manufacturer that I had about how much the people that work there actually decide what they're willing to do and what they're not willing to do. So there's moments where, they encounter a really fascinating project, but the people that work in the factory, they're just like, no, this is, we're going to have that thing laying around. I don't know. I have to bend the steel in ways that I never did it before. And so I think being aware from the very beginning on how and this is part of this folding, for example, is like, what kind of labor do you produce when you produce this machine? Like, how much skill do they have to have? How much do they have to understand the material? And I think quite often the idea behind that is to devalue the labor, to say, like, we make it, and we have the same conversations. Let's make it so it's foolproof. That's more or less the sentence. And I actually think perhaps that's the wrong way, right? Perhaps it's more a question about, like, what's the pedagogical model that comes with the machine to, like, increase knowledge. Perhaps is a better way to think about that.
I like the idea in your presentation that, I don't think you put it exactly like this, but that there is digital craft, that in the same way that, a stonemason understands how the chisel is interacting with the stone, that when students go through this process, or when you go through this process, you learn by failing forward, what the possibilities of the material are, and what the kind of digital craft is. I think the same issue with the 3D printing, right? That you have to understand very clearly what the process is and what how the outcomes are related to the conditions that they're being put in. Flipping that around just a little bit, and then we'll open up for questions. I thought a couple of you touched, and Caitlin, your research, of course, deals with this explicitly, the idea that concrete is a material that we can squeeze much more performance out of. And it struck me the parallels with aluminum, right? When students learn about how toxic aluminum is in the environment, they say, well, we won't do anything with aluminum. You have to explain to them that you can do 100 times with a pound of aluminum what you can do with a pound of anything else, right? So it's a kind of necessary evil almost. And so I'm curious where the next squeeze comes from, right? How do we get the most performance out of concrete? I think, Ted, your argument is sort of like, we are already getting an enormous amount of performance out of it. But where do you see in 10 or 15 years, where is the algae cement coming from? Or, what's the next iteration of clever structural forms, or the processes that eliminate waste and maximize efficiency?
I was really enthralled by Caitlin's presentation on the structures that obviate the need for air conditioning. So it's not about getting more performance from concrete. It's about demanding less performance from other things. If that technology lessens the heat island effect, and we need less electricity, and the compound benefits of no AC is huge, especially in a heating up planet. I don't know. I thought that was fascinating.
I mean, I'm usually struck by this, again, idea that none of these things are new. I think, a lot of the thinkers 100 years ago kind of were onto some of these ideas of how do I integrate systems and think hierarchically across scales and holistically. And yet, I think the reason we stopped doing that, well, I'm curious about what the reason is, but I think one of the reasons was a sort of short-term view of efficiency and productivity that sort of modularized everyone's expertise and forced us to have these very skinny APIs that we communicate against. And then it becomes harder to find those opportunities or to convince anyone that it's an economically good idea because we have such narrow areas that we're allowed to work in. So I agree. I think there's a lot of opportunity, but it's also part of a educational and cultural overhaul that we need to make to enable more holistic and integrated thinking.
Yeah, I'm going to pull on a thread that you started there, which is, what about all the other aspects that concrete is involved with, that it has to function in a building? And a lot of times when you're, specifying a concrete slab, it has nothing to do with structural engineering from the start. It has everything to do with fire ratings. It has everything to do with acoustics. It has minimum thicknesses so that you can fit your plumbing into that slab. And there's all of these non-structural things that are baked into that, magic 8-inch dimension of a flat plate that you see everywhere. And so a question is like, okay, well, maybe you challenge, do you really need so much air conditioning, or what that looks like? And there's been a lot of, development recently in fire engineering. And, a question might be, are we over-designing these buildings for the risk of fire when perhaps other systems that we have brought in have so reduced the risk that we're being too conservative and putting way too much carbon and cost into our buildings because of fire. And so, we recently, did a lot of fire engineering to remove cementitious fireproofing from a large steel structure that we've been working on. And so I think a lot of these really super thin concrete elements that you see, the challenges you start running into are not that of the structure. It is fire, it is acoustics, it is MEP integration. And so having innovations with those other trades will allow that structural trade to, fulfill its potential of optimization.
There was one other thing that really caught me, the business that has those interchangeable parts, right? I was talking to somebody at Wholesome, and I think you're probably referring to that. It's like, well, over time, we are thinking of owning the parts to a building so that when the building comes down, it's just disassembled, and we still own those parts, and somebody could rent them again for another 50 or 60 years for their building.
That is a business model, right? So that's how scaffolding companies work and tent rentals. There's a lot of short-term businesses that I don't think we think that much about, but that do operate in that way and have a skilled labor force. And so I don't think it's totally, the problem is the lifetime, right? No one's going to be around 50 years later. So yeah, it's fun. It's interesting to think about.
That's the only way the Crystal Palace got built.
Oh yeah?
Is its contractor owned all the pieces and was able to take it down and rebuild it in South London and profit off of the building going forward. We do, I think, have time for some questions. I'm looking at Stuart. Yeah, from the floor.
I'd like to go back a couple of months if possible. I'm always impressed with Roman engineering. I'm a little short on volcanic material in Chicago, but for the areas of the world where it does exist, is there any thought to go back to some of the Roman material science and use that material to create what seems to be very strong concrete?
Yes, I mean, I've certainly heard about this and people kind of looking into self-healing concretes as well. I haven't done enough firsthand research to give a definitive answer on that, but certainly there's been a lot of thought around that because of the longevity of the material. The challenge, is that the use and the techniques, are very much different. Specifically reinforcing. It's the funniest thing about reinforced concrete is that if you don't want your concrete to crack, don't put any rebar in it. Because once you put a piece of rebar in it and the concrete shrinks as it cures, it will cause a crack. So a lot of times when you're trying to do really high-end architectural concrete, just get the rebar out of there, will actually improve its condition. And so there may be other reasons as to why I've not seen that more widespread, but I have heard talks on that. I'm not sure if any of the other panelists have some better information on that.
Well, I mean, one of the efforts with all the, fly ash and all of that is to kind of act in a similar way, to use natural or byproducts to reduce, that have a similar kind of act in a similar way as cement, kind of cementous way of operating within the mix, that then replace the cement. So a lot of effort from the research goes into trying to replace the cement with other materials that act in a similar way. Because obviously the large energy is spent in actually the cement production itself, the kilns that burn the limestone, the marble, and all that.
I think it is also an interesting question to ask now, because this, I mean, Ted, you know a lot more about this than I do, but my understanding is, the standardization of Portland cement and its global proliferation was in many ways a political act that happened in the second half of the 20th century and was enshrined in building codes that were mostly created by former colonizers in many parts of the world, and demanded the use of Portland cement, which was almost always imported, which was extremely expensive, which continues to be much more expensive than any locally available materials. I think cement costs 5 or 6 times more in some parts of the world than it does in the United States. And so the idea that there are these alternative materials that exist naturally or are available locally and could play a similar role is really timely to consider, not only for the sustainability arguments, but for sort of supporting local economies. I think there are open questions about the chemistry and the science that people are working on, but I know a lot of people are really working to change their local codes in order to allow for that.
It seems like the crystalline structure that really supported the development
Yeah,
concrete
yeah.
has been discovered.
Right,
So the chemical engineer about 4 years ago, I think, published that.
Yeah.
And it should also indicate why saltwater could erode it and actually make it stronger. It's really interesting.
There's a political dimension to that, I think, which is important, which is the cement and concrete industries are in transition. They go through different periods where they're consolidating and then disaggregating, no pun intended. And it's in the interest of the concrete batch plant business to have as strong a hammer against the cement companies as possible. And so they're very interested in these alternate materials and support alternate materials like the glass pozzolan that you were mentioning. With the demise of coal-fired power plants in the United States, the supply of fly ash is going down, which means that these batch plants are getting even more aggressive about finding local materials like pumice in the West, slag in the Midwest, and others. And those get you very close to the pozzolanic qualities of the Roman cement, and they want to get as close as possible.
So we're at time, and I assume there are some concluding remarks to be had. So I want to thank our panel very much for good presentations, but also a good discussion, and for great work that's pointing us forward, hopefully. So thanks to all of you.
We actually have 0 concluding remarks.
I looked at him and I was
Yeah,
like,
we're like, yeah. So, but we want to thank you for coming out. Thank you to our speakers. I never want to hear the word concrete again, but I have learned so much, and I couldn't have asked for more of coming out of thinking about this one thing, but at such different angles. I think that has just been utterly fascinating, and so thank you so much for coming from near and far and entertaining this conversation that to some, questioned even the premise, and to others seemed like an obvious question. I think that we came to this with maybe not so much a thesis, but a series of questions, and I think that thank you for entertaining those questions, and I think that we didn't come up with any answers, but I think we came up with a lot of different plausible ways of alternate ways of thinking. And I think that that has been a really incredible journey throughout the last couple days. And so thank you very much. Enjoy the rest of your day. It's beautiful outside.
Take some food.
Take some food. There's lots. And we'll see you around. We'll see you around. Thank you so much.